All right, let's dive right into this. Welcome to today's explainer, where we're going to completely decode the chemistry behind water hardness. We've all heard the terms hard and soft water tossed around, right? But what do they actually mean on a molecular level? Well, today we are walking through a complete laboratory experiment, originally presented by Dr. Chem, to determine the exact hardness of a water sample. From the basic chemical theory to the physical materials, and right down to the final mathematical formulas, we're going to see exactly how chemists measure what's hiding inside our tap water.
Here's our roadmap for today's analysis. 1. The theory of hard water. 2. Lab materials and chemicals. 3. The titration procedure. 4. Calculations and formulas. And 5. Real-world applications. Let's get into it.
Section 1. The theory of hard water. Understanding the chemical culprits.
Have you ever noticed the stark contrast in how everyday soap behaves depending on the water you're using? Soft water forms this rich, bubbly lather super easily. But hard water, it forms a gross, insoluble white scum. Why does this happen? Well, soap is mostly made of sodium salts of fatty acids, like sodium stearate. When you use soap in hard water, the hidden minerals in that water aggressively react with the sodium stearate to form calcium stearate, which is an insoluble precipitate. So instead of getting nice, cleaning suds, your soap literally gets wasted, forming a sticky, cloudy film that just clings to your sink, and worse, your skin.
So the absolutely crucial definition here is this. Total hardness is the sum of the molar concentrations of calcium and magnesium ions present in the water. As groundwater percolates through the earth and rocks like limestone, chalk, or gypsum, it picks up these positively charged ions. Now, it's worth noting that drinking hard water isn't necessarily a bad thing for your health. In fact, these dissolved minerals can actually act as a dietary supplement, giving us essential calcium and magnesium. But while they might be completely fine for our bodies, they wreak absolute havoc on our plumbing.
All right, Section 2. Lab materials and chemicals, setting up the experiment.
Let's meet our chemical cast of characters for the experiment. First up, we've got a 0.01 molar EDTA solution. Think of this as our primary titrant. It's the chemical that's going to actively hunt down and bind to the calcium and magnesium. Next, we need an ammonia buffer to keep the solution stable at a very precise pH of 10. Then a vital component, the areochrome black T indicator. This indicator drives our visual color changes. It's kind of like the alarm bell that tells us exactly when the chemical reaction is complete. And finally, our sample water. For this test, we'll start with highly purified reverse osmosis water, followed by standard tap water.
Check out this brilliant laboratory titration setup. See that tall, graduated glass tube clamped to the stand? That's the burette. For Dr. Chem's experiment, this burette is carefully filled all the way to the 0 mark with our standardized EDTA solution. Directly below it is the conical flask containing our water sample, resting on a stir plate to ensure continuous, even mixing. This vertical setup is absolutely crucial because it allows us to add the EDTA drop by drop into the sample with undeniable precision.
Moving on to Section 3, the titration procedure, step-by-step analysis.
Let's walk through the actual procedure and see how this builds step by step. First, we take our 25 milliliter water sample and add exactly 2.5 milliliters of that pH 10 ammonia buffer. Second, we add just 2 drops of the areochrome black T indicator. The moment those drops hit the water, if there is any calcium or magnesium present, the entire solution instantly turns a deep, vibrant wine red color. Step 3 is where the magic happens. We begin titrating. We open the burette to let the EDTA drip into the flask drop by drop, swirling constantly. The EDTA is actively binding to those hard water minerals. We keep adding drops, watching incredibly closely, waiting for the exact moment when the very last mineral ion is bound up.
And this brilliantly illustrates the exact visual moment we're looking for. Notice the dramatic color shift. The flask on the left shows that initial wine red color, meaning hardness ions are present. But once enough EDTA has been added to bind every single calcium and magnesium ion, the areochrome black T indicator is suddenly freed. When that happens, the solution instantly snaps to a clear, bright blue, just like the flask on the right. Bam! That is our titration endpoint. For Dr. Chem's test on the highly purified RO water, this dramatic color change occurred incredibly fast after adding a mere 0.3 milliliters of EDTA from the burette.
Section 4, calculations and formulas, solving the math puzzle.
We can treat this whole thing exactly like a mathematical puzzle by using the fundamental titration formula. M1 times V1 equals M2 times V2. Let's map out our known variables from the RO water experiment. M1 is the molarity of our EDTA solution, which was standardized at 0.0101 molar.
V1 is the volume of EDTA we just used to reach that blue endpoint, which, remember, was 0.3 milliliters. V2 is our starting sample volume, which was 25 milliliters. Our only unknown piece of the puzzle here is M2, the molarity of the sample water itself. By algebraically rearranging the formula to solve for M2, we find that the molarity of the sample is 0.00011212 molar.
Actually, scratch that. Outside of a chemistry lab, nobody really talks about water quality in terms of raw molarity, right? To make this data universally useful, we need one final calculation step to convert that molarity into milligrams per liter, also commonly known as parts per million, or ppm, of calcium carbonate. The conversion formula is pretty straightforward. We take the molarity of our sample, multiply it by the molar mass of calcium carbonate, which is conveniently rounded to 100, and then multiply by 1,000 to convert grams into milligrams. This gives us our final standardized number.
Plug those numbers in, and here's our final calculated result for the RO water. 9.252 milligrams per liter, or roughly 9.2 parts per million. That's an incredibly low number, which makes perfect sense for reverse osmosis water, since the filtration membrane is literally designed to strip almost all the minerals out. But to put that 9.2 into wild perspective for a second, when Dr. Chem ran this exact same titration procedure on a regular tap water sample, the results were astonishing. The tap water didn't require a tiny 0.3 milliliters of EDTA, it required so much titrant that the final calculation hit a shocking 427 parts per million. No way, right?
Section 5. Real-world applications. What these numbers mean for you. Let's put those results into context using the official classification scale from the U.S. Geological Survey. Anything from 0 to 60 parts per million is officially classified as soft. So our RO water sample sitting at 9.2 ppm is safely, deeply in the soft category. But look at the very bottom of the table. Anything over 181 parts per million is designated as very hard. That means the tap water sample we just mentioned, hitting 427 ppm, it isn't just hard, it is extremely off-the-charts, very hard water.
And this brings us to why this entire explainer matters to you and me. When water is that hard, it inflicts severe physical damage on your home over time. As hard water is heated or allowed to evaporate, it leaves those calcium and magnesium minerals behind as solid, rock-like deposits. You'll see thick scale buildup on the heating elements of your water heaters. You'll start to experience reduced water pressure as minerals slowly accumulate and choke the inner walls of your plumbing pipes. Your appliances like kettles and dishwashers will suffer a massive drop in efficiency, meaning they consume way more electricity just to heat water through a crust of limescale. And on a personal level, it strips the natural oils from your body, leaving you dealing with dry, irritated skin and stiff, unmanageable hair.
As our source material plainly and powerfully states, the calcium and magnesium in hard water creates scale buildup. This scale buildup can take years off the life of your appliances. This is exactly why we measure it. This isn't just a minor aesthetic annoyance about soap scum. It's a major economic issue. Ignoring hard water means your household appliances are forced to work harder, they break down faster, and they require early replacement, all of which drastically drives up your home maintenance costs.
Which brings us to our final thought. We've traveled from the macro effects of destroyed soap lather down into the micro world of chemical titration, watched an indicator shift from red to blue, and calculated exactly how many minerals are hiding in a water sample. But the most important question isn't about the water in Dr. Chem's lab. If a seemingly normal tap water sample can hit 427 parts per million and silently destroy household appliances, what exactly is flowing through your pipes right now? It might just be time to do a little chemistry of your own and find out. Thanks for joining me on this explainer. Keep asking questions and stay curious.